retomando, então, os trabalhos. Nós vamos ter o prazer de receber agora o engenheiro Hans Conrads, CEO da PROMECON, Alemanha, reconhecido globalmente, traz soluções aplicadas à eficiência energética em grandes plantas industriais e que vai nos agraciar hoje falando sobre eficiência energética elétrica para processo de geração de calor e energia. Como reduzir o consumo de energia elétrica com foco em eficiência de grandes ventiladores. Temos um fone ali fora, então é só retirar o fonezinho, porque a palestra será em inglês.
Vale a pena.
Yeah, just give him some time to pick up some. That's fine. Thank you very much. Obrigado. Okay. Well, thank you very much for coming here. Thank you for your time. I know that you also have other things to do. Very happy to be here. First of all, I would like to say thank you to Carlos, C2E in Brazil, for providing this wonderful venue and also inviting all the people. Also for providing us the access to the Centec show, which was great. And today, indeed, I want to talk about optimization of thermal process. And the focus will be on process gas flow. Now, this is a very wide field. When I read the title, I said you can actually talk many days about this because there are many types of optimization you can do. So I will try to pick out some important process parameters in some industries that might be of interest to you. Now, I would like, before I start, maybe you can raise your hand if I call up certain industries. Anyone from the cement industry here? Anyone from pulp and paper? Okay. Anyone from glass? No one from glass. Anyone from power? Which other industries come to mind? Steel making, metallurgy. Okay, very interesting. So I could actually talk for several hours now, but I will try to reduce it to the most important points. Steel industry is a special thing because I'm going to talk mostly about combustion. I'm going to talk about fan power reduction. I'm going to talk about dedusting. In the steel industry, we also have a product for the hot part on the electric arc furnace, on the BOF, where we directly measure the oven gas. This is a completely different animal. Do online analysis plus the gas flow. So that I cannot cover today, but of course there will be a big portion in the steel industry also on energy saving. Our company is basically doing process gas flow measurement. That's pretty much our DNA. We do process gas. We were started in 1995, so we have a 30-year anniversary, and tonight we'll have a little bit party with some of our partners that joined us here from South America. And we are located not far away from the city of Berlin, in about 1 hour west of Berlin in Germany. And we are providing the measurement of process gas for these industries that you can see here. Basically, we started in power generation, measuring the combustion air to large boilers, to large furnaces. But also, we expanded our activities to cement, to lime production, to steel, but also to non-ferrous metallurgy, so copper, zinc, lead. The main industries that we have been into so far are basically power, steel, and cement. This is the big one. But when I say power, it's also boilers, industrial boilers. So if you have a paper plant, you have a black liquor boiler or whatever, that would be a similar thing. Waste heat recovery boiler, same thing, right? And you can see we have been focusing a lot on Europe, a lot on North America. You can see that South America is still a very blank spot on the map. And I'm here today to change that. We would like to sell more in South America. Brazil is a very big economy, but other economies as well are very highly attractive to us. Now, I would like to, first of all, address a little bit more precisely what is process gas. You can define anything as process gas. For us, it means gas that has high temperature, gas that contains particulate matter, so dust or some medium, and gas that goes through large duct. When I say large duct, I mean large cross-section in relation to the length of the pipe. Why is that typical? Because usually in the heavy industries, you move a lot of gas, you move a lot of air, and you move this air at a very low density because it's very hot. So you need very big piping to transport that. And if you want to know how much goes through that pipe, simple question, very difficult answer. It's very difficult to measure process gas. We just had a project in South Africa where somebody had an 800 megawatt boiler, and they said, we would like to know how much gas comes out of this boiler. This is a monster issue. It's a huge project. You have to measure 30, 40 points. You have big congestion of fly ash in the gas. And of course, if you want to look at the boiler efficiency, you have to get accuracies way below 1%. Very difficult, right? And in all other processes, it's very similar. So that's really what we have specialized in over the lifetime of our company. And this is just one example. There are many others, but a very prominent example. You have a large boiler. You would like to put combustion air into your boiler. In order to have a high efficiency, you preheat the gas or the air with a rotary air heater. Now, the rotary air heater puts the heat from the flue gas back into your fresh air. But it also puts a lot of ash and dust from the flue gas into your air. And so all of a sudden, your air is full of particles. And these particles make it very hard to measure it. How would you normally measure air? Most of the time, people just take a delta P measurement. So they have a venturi, they have an NU bar, they have an airfoil, something where they can use the Bernoulli equation in order to calculate the flow out of the pressure. Now, the typical example for a power station would be you have a venturi, you have a pressure tab upstream the venturi, and you have one pressure tab on the venturi, like right here. And out of the difference, you measure the flow. Now, the thing is that the pressure transmitter gives you a delta P, typically 20 millibar. This is not a lot. That's a very small pressure. The whole thing is floating on the barometric pressure in this room. How much is barometric pressure? It's 1,000 millibar. So you have a very high barometric pressure, and you're just measuring a small difference. Why is that a problem? Well, think of the dust I've been talking about. You have dust in the air. When you turn this boiler on and off, the dust would get cold. It would go below dew point. It would clog. This thing can completely jam. So your impulse line is completely jammed. And now all of a sudden you measure this pressure against barometric pressure. So if one leg is blocked and you have a thunderstorm coming, your barometric pressure changes from 1,030 millibar to 1,010 millibar, 20 millibar. That's the full scale of what you want to see. And now, the biggest problem is, what do your operator in the plant see? They see nothing. They see absolutely nothing. Because this delta P transmitter is going to a controller. This controller has a set point, and it controls the louver dampers so that it always reaches set point. So you have 20 pipes. You see 20 times the same reading, but it's all wrong. Let me show you. This is from a power station in Berlin. It's a coal-fired power station, 360 megawatts. This is the secondary air to the burner. Now here you can see delta pressure. And someone cleaned the impulse line because the operator could see there is some noise and some vibration. The damper's shutting up and down. Please clean. So they clean. Afterwards, no vibration. But you can see the same level. You have the same level. You have 25,000 norm cubic meters. Everything is fine. But this one, that's the air damper. Before and after cleaning, the air damper has a completely different position. What does it tell you? It tells you that this value is wrong. This should have been much lower, right? We call this self-fulfilling prophecy. The controller always controls to set point, so your operators cannot see it. If I go to a power station with 20 secondary air readings, then I'll see that the dampers are all over the place. And the flames are all different. Every burner has a different problem. And that's because all of the airflows are wrong. And this is what's costing you a lot of energy. It doesn't matter which process. If you go to a cement plant, you have a large mill, same problem. The raw mill has some airflow. Is it correct? Who knows? So that's the first issue that you have with process gas. And even in other processes, if it's now pulp and paper, heat recovery boiler, whether it's in cement, whether it's in metallurgical applications, you would like to know the flow? Bad luck. Most of the people have big calculations that take some static pressures, some temperatures, and then they try to make up a balance to find out what could go through this pipe. Make your life easy. Just measure it. Yeah? But you need something that works, and that's the big problem. Usually you have this drift problem. Another thing, just as an example, a very modern Alstom boiler, 800 megawatts, brand new, same problem. The red line is delta P, before and after cleaning, same level. Here you can see how bad it can get with the swings. And then the blue line is your air damper, higher, lower. So definitely there is a measurement problem here. And this is our measurement, higher, lower, because our measurement doesn't drift. Our measurement is a digital flow measurement that will never drift. Our measurement holds the calibration over the life of the system. If you buy this system, you will never have to recalibrate it. Yeah. And I will explain in a minute why. But before I do that, I would also like to show you this typical problem that you have with dampers when you regulate process gas flows. If the impulse line is very long, it can happen that it blocks the air so effectively that it takes a long time before the impulse really reaches the DP sensor. During that time, the damper opens up more and more and more. And finally, when the air gets to the sensor, the damper shuts down again. So you get this typical swing. And if you look at these, here and here, you can see that the phase angle between the two is 90 degrees. It's a perfect resonance condition, right? If you clean the impulse line, it's gone. Now again, all this trouble you don't have if you go to a digital measurement that does not use impulse lines, that does not use delta P. And I'm going to show you a little bit in a while. Another problem I would like to mention with process gas and big ducts, you usually have swirl in your duct. It's a very natural thing to occur. The swirl of the gas does not only come from your fans because they're spinning, but it comes naturally from the way that your ducting is routed. This is an example of a power station in South Africa. It's a very big boiler, combustion engineering. You have a very big bulk duct that comes out, basically comes out of the screen. And then the gas goes upwards, or it goes sideways and upwards. And what happens, you can see here, in this manifold, the gas only turns one dimension. In the other manifolds, the gas flow turns, or the pipe turns two dimensions. It turns up, sideways, in this way. And you can already see this is a screw movement. Now the gas has a mass, the gas has an inertia, the gas does not want to follow this, so it spins counterwise. So in many ducts you have spin, here, here. Here the spin is lower. You never know how much spin you have. So if you want to measure process gas flow, for example, into a big fan, you must have a measurement that only measures the gas as a vector. You only want to know the amount of velocity in the direction of your duct. You are not interested in lateral spin or whatever. So drift-free, digital vector measurement. That's what we do. That's what you need for process gas. I'm going to show you in a second how we do that. As I mentioned, our measurement is digital, drift-free, and it measures the flow as a vector. So you will always see the true mass flow that goes through the duct instead of some spin or some stratification that you have. How does our measurement work? Our measurement does not use delta P. It also does not use any heat dissipation like hot wire anemometers. Our measurement is basically clocking out how fast your gas is traveling. And for this, we use two principles. The first one is the generation of an electrostatic signal. So we need to have some signal that is the basis for our measurement. The second thing is that we have a cross-correlation between two signals that we take. And this cross-correlation then calculates you the time of flight of the gas. Let's go into it. First of all, we have a sensor inside the gas duct. Now the gas duct carries a lot of particles, and these ash or dust particles are electrostatically charged. The electrostatic charge causes a mirror charge on the sensor. Some of you might have heard of Coulomb's law. The total amount of charge over this whole area must be neutral. So if your cloud has a slightly positive charge, your antenna will have a slightly negative charge. Now, as the gas flow progresses, you will have clouds of positive and negative charge flowing by your sensor. So you will have a change of charge over time. What is change of charge over time? It's electrical current, right? So you just measure an electrical current over time. Why is that so important? The clouds of dust that come over your sensor are basically random. So you don't see any function, you see a random. It's like a fingerprint. It's like a very characteristic signal that you can see here. We call this a time signature. In the next second, there will be a completely different time signature, and then there will be another completely different time signature. So the clouds leave a characteristic signal on your sensor, and that is important because the characteristic signal contains information, right? What information is that? We basically take two sensors in series, sensor 1, sensor 2. If you put them close, like 300 millimeters, then the time signature in a certain time on both sensors will be very similar. The flow pattern does not change within 300 millimeters, right? Let me show you that. There we go. Two sensors, and now you have the dust going by. And this is basically how it looks like. Sensor 1, sensor 2. So both contain the information about how the dust went by the sensors. If you put these two on top of each other, you can see they are very similar. Of course, they are time shifted because the sensors do not sit on the same location, right? You do have a time shift between the two. And that's the whole thing. We are now using basically the two signals to mark a certain time on each sensor. So if you put those two signals into a cross-correlation filter, you will get a cross-correlation function. What is that function? This correlation function measures the overlap of the sensors. How much is the overlap? You can see here the overlap is not very big. But if you shift the two functions, you will get to a point where the overlap has a maximum, right? And that means at a certain point in time, we know the time of flight from one sensor to the other. We're just clocking it out. And by this measurement, the dust, which is usually the natural enemy of flow measurement, becomes our tracer. We trace the gas velocity by the dust. Yeah. The big advantage of this measurement, of course, is that you have a digitized signal. The only variable that you have is time. Yeah, so you have the two sensors with a fixed distance, and you measure time shift. And time is the most accurate measurement that mankind ever invented. There's no doubt about time. So that's the reason why once you have this, you will never see a drift. You will never have to adjust for zero, right? If the velocity is zero, the time from sensor 1 to sensor 2 is infinite. There is no zero. So it's a very linear calculation of flow. So what you then do, you multiply the velocity with the cross-sectional area of the duct. That gives you actual flow. And then you compensate for barometric pressure and temperature. And then that gives you a standardized flow. Yeah, very simple. We've applied this to thousands of process gas pipes with temperatures from 100 degrees Celsius up to 1,000 degrees Celsius. We also have an optical version of this, which can go up to 2,000 degrees Celsius. So if you want to measure, for example, a tertiary air duct with 1,200 degrees, it's no problem. You can put this also with an optical sensor, infrared sensor, it's the same. So the typical thing that you have to purge and clean the delta P measurement, you don't have with PROMECON. Our system will run. And we have several clients that forgot about where the sensors are positioned because they never have to look after them. The sensors are in the process and they stay there. And that's the biggest advantage of this. Now, I've explained digital and drift-free. What about vector? What about the fact that we're measuring a vector? It's very simple to explain. We are measuring a time shift. Now, you might say a time shift is a scalar value. There's no vector in time. But we divide the distance of the two sensors over time, and the distance is a vector. What distance do we mean? We mean the vector that is orthogonal or perpendicular on the two sensors. Right? If you have a flow that it goes this direction, we will only give you the velocity in that direction, nothing else. Yeah? So you have a directed flow, and our measurement by this reason is insensitive to swirl. And this is very, very basic. If you have for a delta P measurement, or you have a nozzle, or you have a pitot tube, and you have swirl, you can be off by 20%. And nobody can tell you why. Right? Let me show you this. That typical swirl, you would have a swirled flow. The swirled flow is not what we see. We see only this. That's it. Yeah. Especially in stacks. We had an audit by Deutsche TÜV Süd, and they told us it's the most accurate measurement in the stack they've ever tested, because it's not sensitive. On each stack, you have a large fan, an ID fan, which swirls the air around. If you look at the plume of the stack, you can see that it sometimes swirls out. There's always swirl in a stack. And I would say 90% of the cheap pitot measurements in a stack are completely wrong. Nobody can check it. No? So that's the big advantage of measuring a vector. Now, I would like to go into typical applications, and I must say there are so many applications that maybe you have to help me come up with some good new ideas. The main applications that we have done, I can show you, and I can show you what people can do with it. First of all, we have to remember that moving air around in heavy industry is a big cost factor. take a cement plant, if you take the grinding plant, the amount of energy that you need for all this, half of the energy is used for fans. Half of it. Yeah? So forget the grinding power and all that. It's just moving air from A to B. If you have a large raw mill, you can have a fan of a megawatt. Or if you have power stations, you have an ID fan with 5 megawatts. Just, whoop, was that? Oh, let me just see if I can fix it. Okay. So in a power station, where is the airflow of importance? The airflow is of importance here when you put the air into your pulverizer. What if you have a wrong airflow into your pulverizer? You have the wrong grinding because you blow the coal out too fast. Yeah. You have the wrong transport velocity of your coal from the pulverizer to your burner. Huge amounts of problems that originate. And I can make a bet, if anyone has a coal-fired power station, you send me the printout, the screenshots of your current mill with airflow, delta temperature, and coal flow, and I will prove to you that at least 1 or 2 mills are wrong. It's very easy. You make a mass energy balance over the mill, and you see not every mill is the same. And the reason is that your airflow is wrong. Airflow is a very big culprit in this whole thing. It continues. Secondary airflow on the burner. Yeah, you have burners that are producing CO, and they're producing other burners producing high NOx. So you have a boiler with high NOx and high CO at the same time. Yeah. Why? We heard the Enotech. Enotech is checking the O2 at the end of the boiler. Of course, this has to be correct. It's very important. But very often, the big problem is upstream. You have 20 burners, some of them like this, some of them are like that. You have, and nobody can check this. Yeah. And that's the second big problem. So if people would like to cut back on O2, you make the excess air lower on your boiler to save money. You know, making the excess air lower by 5%, from 20% to 15%, saves you $2 million a year on a large 600-800 megawatt unit. These are gigantic savings. Half of the saving coal, the other half fan power. Just reduce fan power. But you cannot do that without having unburned carbon, CO going through the roof. And why? Because some burners are running in the wrong stoichiometry. They don't have the right airflow. Some are too high, some are too low. You have to level out this, burner by burner. That's the reason why secondary airflow is so important. Flue gas flow. Imagine you have 2 lanes of flue gas, 2 ID fans, and both ID fans run at the same rating. But magically, one lane is pulling more gas than the other lane. What's your problem then? Well, first of all, again, it's fan power, because the fans are not symmetrical. You could put one fan lower, that would be possible. The other one is particulate emission, because one lane pulls more gas than the other. So you have a much lower separation degree on one lane. Yeah. I would say power stations are a super example of what can go wrong with airflow. And I can say after 30 years in this business, airflow is the most neglected measurement in power stations. Because everybody tries to get it right. They have an O2 measurement at the end, which is of course important, very important, but they don't know what's happening inside the boiler. Big problem. I'm not sure how far this applies, but when you looking at waste to energy plants, it's the very same thing. You have an undergrade air, and very often people don't know when you have the burning grate, where does the air come through? You have high air flow here, low air flow there, you have hot spots, you have NOx problems, you have higher wear rate on your grate, yeah? So all sorts of problems. And then of course, measuring the raw gas into your scrubber units and into your flue gas cleaning systems. Nobody measures this. but it would be very important. Yeah, people don't do this because it's so difficult to do. And then, of course, cement plants. Don't get me started. Cement plants are moving so much gas around. Let's start at the beginning, the raw mill. I would say in many cement plants, the raw mill is overdrafted. Yeah, when the gas flow in a cement in a raw mill, these raw mills are big. I'm not sure if you're all familiar with cement plants. These raw mills, they grind 300 tons of raw meal per hour. They are high as a 5-story house. It's unbelievable. And if you have not enough air in the raw mill, your raw mill can trip. And then you have a huge amount of raw meal lying on the bottom of a mill that you have to get rid of. It's the monster thing that nobody wants to have. Big problem. Yeah. Usually it's, if you have, how much material would that be if the mill trips? It's usually 5% of the hourly throughput. So if you have 200 tons and it trips, you have 10 tons of raw meal that you have to get rid of. So operators like to overdraft the mill. It's better to put more air through the mill than necessary. Now we all learn the fans that are pulling the air through the mill, the power consumption goes up to by the third order of flow. Right? If you pull 10% too much gas through the mill, you are like 27, 28% too much electrical power. And with a fan, that is a megawatt. So that is a big issue. You can save huge amounts. Then, of course, it goes on. The main problem here on the downcomer. At this location, it also ends up in another ID fan. You want to know where the gas goes and how much gas you're putting through the kiln. Super example, we had one guy from Enotech today talk about this fancy O2 measurement on the kiln, which is here. This is a very important measurement to keep the kiln atmosphere correct at the right level. But this measurement is very slow. You will still have a lot of fluctuation on the control of the kiln because you don't know the exact amount of gas flow down here. Right? And the result is that the fan will go up and down. And as we know, the fan power consumption goes up non-linear. So every movement up and down is losing energy a lot. You want to run the fan flat. And what cement companies are doing is they are using the O2 measurement here, and they're using our measurement there, and they make a cascaded controller. So they have a long-term controls based on the O2. They have a short-term controls based on our. And then they can run the mill flat over a long period of time. That's one of the most common applications we have for Holcim Lafarge. They've done dozens of these. And they all have an O2 measurement down here. So they're both necessary, but it's an optimization to get the process optimized. Then we can measure tertiary air here. So we can measure the total combustion air that goes into your pre-calciner. Any problems with high NOx on your cement plants? Well, check your pre-calciner. The pre-calciner has fuel, and it has a huge amount of combustion air coming from the tertiary air. Nobody measures it. Why? It contains dust, very abrasive dust. It's clinker. It's 1,000 degrees hot. How can you measure this? We have installed many tertiary air measurements in order to optimize the mixture of tertiary air with the fuel in the pre-calciner. And then we can also measure the total air balance over the clinker cooler. So you can optimize clinker cooling. And waste heat recovery is another thing. These are the most popular ones. There will be more. There's bypass measurement. In a cement plant, there's gazillions of things. But the typical application would be also for boilers, heat recovery boilers, or for any refining process that you have. Copper plants, roasting, calcining, refining. In all these steps, you would like to know how much flue gas am I putting out of my process and how can I optimize dedusting, fan power. Here we come to the steel industry. Steel industry really falls into two fields. One is the cold side, which I'm talking about today. Cold side is anything up to 600 degrees C. And the hot side, which is this one, that is up to 2000 degrees C. In the cold side is mainly the primary, secondary dedusting. Typical application, you have an ID fan. You have 2, 3, 4 ducts that are coming into the ID fan from all sorts of parts of the process. On all these ducts, the dust level is not constant. Sometimes it's high, sometimes it's low. But usually this fan is pulling all the time. So you're putting way too much gas through your cleaning system. Why is that bad? Particulate emission, number one. Fan power, number two. So if you have a better handle on how much goes through each of these ducts, you can manage and reduce the total flow significantly. And by that, lower fan power, lower your emissions. On this side, again, I could have another presentation on that. We have developed a system that can measure the flow out of the furnace and that can measure the gas composition out of the furnace. So we can tell you how much CO and how much CO2 comes out of this furnace. Why is this important? The operator of the furnace can see how much carbon comes out of his furnace, and he can reduce the power on time of the furnace. He can reduce CH4 injection. He can reduce carbon injection. This is a monster thing. If you can optimize the furnace, you save $5 million, $6 million per year on an EAF. We have one EAF specialist here today with PROMECON, so if you have interest in that, we could have him because he will be able to tell you everything about this. It's currently a very, very big product. Very, very big. So I would like to show you how this looks like. How does the measurement look like? This is a big power station that had a typical Venturi, and they had the drift problem that I was talking about in the beginning. So the air distribution in the boiler was wrong. The total gas flow through the boiler had to be kept at a too high safety margin, and by that the plant was suffering high energy loss on the fans. We installed our sensors here. There's a retrofit, and these are the boxes. This had to be all SIL 2, so the whole measurement is SIL 2 certified because of boiler safety and everything. And client very happy. We've installed these on many boilers worldwide in order to get rid of the problem of drifting flows. Here another example where a new boiler from Mitsubishi Hitachi was retrofitted, or not retrofitted, it was equipped with our system from the beginning because the client insisted on this measurement instead of the old technology. And then here, this is a very big project we did in Chile many years ago. There was a big problem that Electricity that Chile had with its boilers. They wanted to optimize the output of the boiler and the efficiency. And for this, they needed to measure the total gas flow out of the boiler. This is these are the monster projects on gas flow, because look at how short these pipes are. Yeah, and you have to be able to measure them very, very precisely. And this is the typical measurement. This is the load of the unit, and these are the two, the left and the right side. And you can then take the average and see if they're exactly on top of each other. If you have differences of about 1 or 2%, that's an issue. That's already an issue. It's not an issue on a single burner, but if you have the total flow coming out of the boiler on the left and right side, then of course these small percentages represent a large difference in flow through each precipitator. Why is that such a problem? Here another example. Another application, by the way, for this is to test your scrubbers. We have a big project in South Africa where the scrubbers are falling apart, and there's a huge fight between the boiler maker and the flue gas cleaning engineering company who made the mistake. And the engineering company says the gas flow out of your boiler is higher than the specification. You put more gas through your boiler. Your boilers are basically too small. And the result is that the flue gas scrubber gets too much gas, it can't clean it. So part of the lime injected is blown out at the other end, and it settles in the chimney duct, and the duct falls down, and it's just a disaster. So we had to measure very clearly how much goes through. And of course, they want to know it down to the percent over a long time. And without a digital flow meter, you can't do this. This is the only way to do it. And frankly, I would say we're pretty much the only company in the world who can do this over a longer period of time, because you need this technology to do it. And of course, the big issue is how do they find it? This is when you talk to fan companies, you know, you talk to Howden, or you talk to Venti Ulde or TLT Turbo. None of these fan companies have an idea of where their fans are operated on the fan curve, because they have no way of measuring the flow through their fan correctly. This is very, very difficult. If you have a power station and you have a big ID fan, and the gas flow hits the ID fan just with a slight spin, and the spin is the opposite direction of the fan rotation, your fan performance goes all the way down. Now, how do you measure spin? How do you prove that? And there's huge fights over this. And the other thing is, of course, you can see it very nicely. This is the typical points on the fan curve, and you can see it's going up non-linear. So checking your fans is a huge resource of saving energy, saving electricity. Again, one of the most neglected areas. And it's, if you take a plant, you will find the most amazing flows. Right? And of course, it's an unseen problem, and it goes along with usually fan operation that is wasting energy, that is not correct. It can be as bad as replacing your fan wheel with a fan wheel that is better. But even with new plants, very often there's a big fight, because the fan curve is not only depending on the inner fan curve, but also on the system curve, which means the curve that comes from your plant, from your ducts. And very often there is a mismatch that is not projected correctly. And the only way to find out is to measure, right? To measure is to know. If you can't measure it, you're stuck. There's no way to put it. So this is a little bit out of the spectrum of what we have been doing in the past 30 years. There are many more interesting and exciting applications, but I think measuring process gas is something that is always connected to very high leverage of savings. And it's worthwhile to look into the process deep enough. And I think the field of business for us is growing, and it's so vast, because there's nearly nobody is taking care of this measurement. But it's usually a very crucial point of your operation. Now here comes the advertisement part. Our certificates. Let me just see. Help me. Technical spec. It reads a bit like measurement principle cross correlation, measurement range 0, I would say, not 0, I would say 2 meters, 2 to 100 meters per second. Now 100 meters per second is a practical limit. With this correlation principle, you could measure transonic. You can measure any up at the high, there's no end in the high velocity. But 100 meters per second is so high. You sometimes see it. If you have a venturi or an airfoil, in the gap of the airfoil is a very good point to measure. We like this. Why? Because the airfoil acts like a flow straightener. So if you have a bend, you have an airfoil, then the profile inside the airfoil is very flat. It's a very good point to measure. But you have very high velocities. You have very low cross section, so there the losses can go up to 60 meters per second. And then no drift, no cleaning, linearity, 100%. Accuracy, that's usually where all measurement companies start to lie. Accuracy. Accuracy depends, of course, on your installation conditions. To be accurate, you need to have a certain representativity of your measurement. And that depends on the stratification of your flow. So you have to get rid of stratification, for example, by an aerofoil or by a venturi. Or you have to have multiple measurements and average correctly. These are the two ways of getting the accuracy right. And what do we do with clients? Usually we ask them to send us a drawing. We have a look at the drawing. We may do a CFD to fit the sensors in the right position. But for many applications, we already know where to put the sensors. We've done this for 30 years and we know how well to position them. Okay, more sensors, more stuff. I won't bother you with that. We'll send you some more details. One thing interesting, this is not a long sensor. This is a sleeve, and there's an infrared diode on top of here. That's our new wonder sensor. We can measure the velocity, but we could also measure chemical composition. Yeah. And chemical composition is not like Durac said, down to ppm, ppb. This is the other end. This is we are measuring percentage. We're measuring 20% CO2, 30% CO. Right? When you have a steel furnace and the temperatures are so high, all the CO2 falls into CO because the high temperature destabilizes the molecules, whatever. So you have excessively high CO. You want to know the CO and the CO2 to make the carbon balance. So this is what we use this for. This is not an emission sensor. Yeah. This is a sensor for process. We are process people. We are not SEMS people. For SEMS, you have to go to Enotech, you have to go to Durac. We are process people. We are only interested in process. The more difficult, the better. We like it very difficult. Okay, that brings me to the end. Thank you very much for listening. I hope I could give you a little bit of a splash. This whole thing is so complex that I could keep on talking forever, but I will stop now, and I will be happy to take some questions if you have.
Thanks, Hans. Quer falar, Carlos?
Eu queria falar só umas palavrinhas sobre a PROMECON. O que me admira bastante é que os sensores resistem a ambientes extremamente agressivos, eu fiquei impressionado com as aplicações que eu já presenciei, com gases extremamente quentes e também bastante pegajosos assim na sonda. Apesar de a sonda parecer contaminada, ela continua recebendo sinais e provendo sinais sempre disponíveis. Outra coisa que me chamou muita atenção em trabalhar com essa empresa é que todo o comissionamento é feito de forma remota. Nós tivemos a internet, colocamos o Team Viewer, nós temos um software específico que é instalado na máquina. A gente também consegue instalar esse software remotamente. E o nosso colega que está lá atrás, que trabalha com o Hans, o Christopher, faz isso de uma forma muito rápida. É interessante que eu trabalho com analisadores há bastante tempo, com medidores de particulado e sensores de chama. É sempre um processo lento de comissionamento. Necessita tempo para comissionar. Existem várias variáveis que você deve observar dentro do comissionamento. E nessa medição digital, essa resposta vem muito rápida. Isso me chamou muita atenção nas aplicações que eu já tive experiência de trabalhar com esses senhores, com essa tecnologia que eu achei fiquei bastante impressionado pelos dados que nós precisamos para fazer a automação de caldeiras e processos e etc. Queria agradecer a presença do nosso amigo Mr. Conrads, que veio diretamente da Alemanha aqui chegou no Brasil quarta-feira, diretamente para estar aqui com a gente hoje. E parabenizado pelos 30 anos de empresa. E eu volto a palavra para Kelly.
One question, I guess. Yeah.
Thank you for your presentation, Conrad. I like this kind of measurement and I understand the quality. My question is that the quality of the flow measurement depends on the correct position of the sensors. Because if you have large ducts, the velocity in one point may be different than in other point. So if someone buys this kind of sensor, he does not know where to install, he will not have a good measurement result.
Yeah, 100% correct. The sensor position needs to be defined correctly. We usually do that for clients. Yeah, imagine you have a downcomer that is like 90 meters. You put it somewhere, but you have a duct that comes around the bend, and then you don't have much space. Where does the sensor go? That's a very legitimate question. Very good question. In many power stations, for example, you have already a venturi or an airfoil where the whole duct is tapering down. And we like to go in this tapered section because this really acts like a flow straightener that forces the profile into a nice, more uniform shape. And that's where we usually put our sensors. If that's impossible, like in the example in South Africa, yeah, we had to place 8 pairs of sensors on the circumference and make them long enough and then average everything up. It's a monster project. So, correct. The analysis of your flow profile is part of the engineering solution for this problem. You can't go without it.
Okay, thank you.
About the coding that Carlos was saying, the code information is not a problem.
Which we say the.
Coding.
No. Oh, okay. This is very important. That's also a very good question. Why, if the sensor gets dirty or there's coating on the sensor, why does it not affect us? Well, it's very simple. There's 2 types of coating. You either have coating that is conductive, or you have coating that is non-conductive. If you have coating that's conductive, it's like making the sensor just a little bit bigger. It's the same thing. There's no difference. If it's non-conductive, the electric field goes through the dielectric coating and still induces a charge on the antenna. And here's the point now. I was talking about this. This is very important. I was talking about this time signature. Yeah? The time signature that we see when we look at the sensor. The information over time is the key thing. The amplitude is not important. The amplitude goes down by a factor of 2. You still have the same time information. And that's why when we have less signal, we still correlate and we still see the right time shift and the right velocity. Yeah? In fact, if you take the signal and you make delta signal over delta t for both signals, you can still correlate them. Same thing. There's no difference. It's just the time information that matters. Right? So that's the reason why the coating will not affect our measurement. It will never drift. If you have a reading, it's going to be a correct reading. One more question, yeah?
Just to complement the question from our colleague here about the straight length requirement for the sensors, if there is any minimal distance from, for example, bends or any other disturbances on the ducts.
Yeah, downstream, I would say nothing. Downstream, there's usually, with delta P, there is a constraint because the bend downstream induces also a different pressure. So downstream, we have no constraint. Upstream, as we discussed, there can be stratification. So if you have a duct, we would need to see a drawing to estimate where the sensors, how many sensors you need and where they should be placed. So that's definitely important. Yeah. So you have to think about where to put them. Measuring these monstrous ducts is something that you have to. There's some engineering part to that, or some application engineering.
More? No. Thanks, Hans.
Thank you very much. Yep.